Recall that an infinite series associated to a sequence is the sequence of partial sums, that we denote a series with sigma notation, and we think of it as an infinite sum. A function series is a series whose terms are functions, and a power series is a function series whose terms are of the form a sub n times x minus c to the n for some sequence a sub n, called the sequence of coefficients, and some number c, called the center of the power series. Let's look at an example. Recall that the geometric series converges to a over 1 minus r whenever the absolute value of r is less than 1. Changing only one letter, we get the sum from n equals 0 to infinity of a times x to the n, which is a power series centered at 0, all of whose coefficients are a. Note that this expression is defined only when the absolute value of x is less than 1. When is a given power series defined? In other words, for what values of x does this series converge? We already know that this geometric series converges on the open interval from -1 to 1 and diverges elsewhere. We also know a closed expression to which it converges, namely a over 1 minus x. The concept of a series converging to a known function is something we'll discuss in another video. Let's go back to our general example. Since for any power series, setting x equal to c yields this series in which all of the terms disappear except the first one, we know that every power series must converge at its center c, no matter what the coefficients are. But where else could it converge? Let's start by looking at two examples. First, consider this series, noting that it's a power series even though we start indexing at n equals 1. We apply the ratio test to these terms, and you can verify that the result simplifies to the absolute value of x. From this we conclude that the series converges when the absolute value of x is less than 1, and diverges when the absolute value of x is greater than 1. We can't conclude anything from this about what happens when the absolute value of x equals 1, so we test those two cases explicitly. When x equals 1, we get the harmonic series, which diverges. When x equals -1, we get the alternating harmonic series, which converges. We conclude that the series converges on the half-open interval from -1 to 1, and diverges everywhere else. Note that this interval is centered at 0, the center of the original series. Second, consider this series. Once again, we apply the ratio test, and you should verify that this simplifies to the absolute value of x minus 4 over 2. So the series converges when the absolute value of x minus 4 is less than 2, and diverges when it's greater than 2. As before, we can't conclude anything yet about what happens when the absolute value of x minus 4 equals 2, so we test those two cases explicitly. When x minus 4 is plus or minus 2, we get this series, which can be simplified to this, which diverges regardless of the sign of x minus 4. Thus, we conclude that the original series converges on the open interval from 2 to 6, and diverges everywhere else. Note that this interval is centered at x equals 4, the center of the original series. These two examples lead us to the following theorem. A power series converges on an interval I of radius r centered at c, and diverges elsewhere. I is called the interval of convergence, and r is called the radius of convergence, which can be any non-negative number or even infinity. Graphically, we see c on the number line, and this power series converges on some interval like this one. This distance is r, the radius of convergence. Note that we might include one or both of the endpoints of the interval. And since we allow r to be infinity, the interval might not have any endpoints at all.